Hi, students. Welcome to our distance lectures. Um, this lecture video is going to take the place of our Monday, April 22nd, and our Wednesday, April 24th classes. So because of this, it's going to be extra long. I hope you guys are having a good week or will have a good week since I don't know at which point you guys are watching this. And so today I'm going to be talking about glaciers and ice ages, which covers chapter 18 of our book. So first, ice ages. You guys might have heard the term ice ages through these movies, or perhaps in another course or whatever. Um, but if we consider the ice age shown in the first movie, not the others, that ice age shown there ended less than 12,000 years ago, which is why there were humans in it. During that ice age, as much as 30% of the land surface was covered by an ice sheet. To compare that with what it is today, currently less than 10% of our land surface is covered in ice. So, a significant amount of land surface was covered in an ice sheet. Ice sheet, as we'll be talking about for the rest of this video, is a layer of ice that is hundreds to thousands of kilometers across and a few kilometers thick. So, ice sheets, now we're going to talk about ice. So, ice, like we've mentioned earlier in this class, is a mineral with a chemical composition of H2O, and it also has a regular crystal structure, which is hexagonal, like snowflakes that we see here. We can think of the natural occurrence of ice and compare it to the natural formation of different rock types. So, for example, we can think of the formation of ice as we would the formation of an igneous rock. Igneous rocks, like we've talked before, form a lot of them form from the cooling of melt underground, and when it cools, it crystallizes like this cup of water, which is crystallizing into ice. We can also think of the formation of ice compared to the formation of a sedimentary rock. So in these images, we can see boundaries between different layers of snowfall, which kind of mimics sedimentary structures that we might see in, like, for example, a sandstone. Finally, we can also compare the formation of ice to the formation of metamorphic rocks. Metamorphic rocks tend to be put under a lot of pressure and temperature, and the same thing happens with ice. We start out with very loose snow, and eventually the accumulation of more snow increases the pressure, which then recrystallizes the ice beneath, which is the same thing that happens in a lot of metamorphic rocks. So now that we've seen how ice forms and we've equated ice to rocks, now let's think of like what specifically is a glacier, because not every time that we have snowfall, we have the formation of a glacier, obviously. So in order to form a glacier, we need a few different things. One of it is that it needs to be cold. And this is kind of a given, but it needs to be cold enough throughout the year, not just during the winter. It needs to allow snow to accumulate even during the summer so it doesn't melt away. Speaking of snowfall, the snowfall rate has to be large. So there needs to be snow falling constantly, or at least a large amount during the year, in order to allow that accumulation. The area needs to have a gentle slope. Although we do have the formation of mountain glaciers that we'll see later, it would be useful if we have like a slope so it doesn't just like fall off and not accumulate in place. And finally, we need to protect it from wind, because if we have our snowfall and then there's like a snow drift and all the snow goes away, well then we don't have the formation of a glacier. Currently, we have glaciers forming in polar regions and mountains, and usually these are the areas where we will have glaciers throughout the geologic record, but not necessarily. So how do we get to a glacier? So when snow first falls, the snow doesn't fit together tightly. We can think of snow as 90% air, so all of that pore space. Over time, the snow starts packing more and more tightly because of the pressure of more snow until it becomes 25% air. When it is 25% air, we would call it firn, but it is still granular. It is still those individual snowflakes that fell in the beginning. However, after this point, there is enough pressure that that firn can now recrystallize into coarser crystals, in which case now we can consider it like a glacier. Um, all of this process can take tens to thousands of years to actually happen. So it doesn't happen like from one day, like from one night to another. We can, so now that we've seen glaciers, now we have our official definition of a glacier, which is a stream or a sheet of recrystallized ice that stays mostly frozen all year long and flows under the influence of gravity. Okay, so um, we have two different kinds of glaciers that form based on their relation to topography and on their overall surface areas. We can have mountain glaciers and we can have continental glaciers. Now let's start to define mountain glaciers. So mountain glaciers, also known as alpine glaciers, exist in or are adjacent to mountainous regions if the temperatures remain cold enough. So mountain glaciers form at higher elevations and then through the movement of the glaciers can flow to lower elevations. Mountain glaciers then are classified based on their shape and position. So here we have different kinds of mountain glaciers, which I'll define, like I'll have better pictures of in the next slide. But we have cirque glaciers, valley glaciers, we can have ice caps, and Piedmont glaciers. So valley glaciers, which is this definition in the middle, are rivers of ice that flow down valleys, which kind of like valley glaciers flow down valleys, self-explanatory. We can have ice caps, which are mounds of ice that are found at like peaks of mountains and at ridges or crests of a mountain range. We can have cirque glaciers, which fill bowl-shaped depressions on the flank of a mountain. And then finally, we can have Piedmont glaciers, which are, we can think of them kind of adjacent to those alluvial fans that we saw earlier, that form when a valley glacier emerges into an adjacent plain. Um, so these are the different kinds of mountain glaciers. Now let's talk about continental glaciers. So continental glaciers are vast ice sheets that spread over thousands of square kilometers of continental crust. They flow outward from their thickest point, where ice can be as thick as 3.5 kilometers, and then they thin towards their margin, where ice is only like a few hundred meters thick. Um, in this image, we're seeing Antarctica, and the different colors correspond to like the thickness of the glacier in Antarctica. And then this red line shows a cross section, and it shows us like it's a difference between the West Antarctica ice sheet and the East Antarctica ice sheet. Earth is not the only planet in our solar system which has the formation of polar ice caps. We also have polar ice caps on Mars. So they consist of H2O as well, but it's also mixed in with dust. And so the formation of them is that during the winter, they have carbon dioxide freezing over the North Pole and covers it with around 1 meter of dry ice. And then the southern pole is much colder, which is covered by 8 meters of, which should be covered by a blanket of 8 meters thick, and it does not disappear during the summer. So Mars also has ice sheets. So now that we've talked about what ice is and different kinds of glaciers, now let's think of how do glaciers move. So ice, like the metamorphic rocks that we talked before, can undergo plastic deformation, which was that kind of like deformation that it was like hot enough that it didn't melt, but it kind of behaved like Play-Doh. So for silicate rocks, this happens like very deep in the crust. For glacial ice, this occurs at about 60 meters depth. And we've talked that glaciers can be kilometers and kilometers, kilometers and kilometers deep, Therefore, most of the glacier can move around plastically. Um, so above this brittle plastic transition line, which is above those 60 meters, ice behaves like a solid, like a porcelain plate, for example. It's too brittle and it doesn't flow. However, below that brittle plastic transition, ice glaciers move around like Play-Doh. And as they move around, they kind of move the part above it, causing it to crack. So you may end up with like crevices like this across a glacier. So why do glaciers move? Well, first, gravity. Gravity is causing glaciers to move, like for example, mountain glaciers moving from a highest point to a lowest point. However, thinking of continental ice sheets, it becomes a little bit more complex. So we have our continental ice sheet, and they flow from their thickest point outwards to thin out. So as more ice starts to accumulate at that thickest point, the basal part of the ice, so the ice at the bottom, can no longer support the overlying ice, and so it starts to deform plastically towards the side, and it carries around the ice with it. So, in this image, it kind of equates this to like honey. So if you have honey, like you're pouring honey over it on a table, and it just kind of starts to like move towards the sides because like it can't handle the extra honey that you keep adding. The other important thing to take out from this image is that since the important part for the moving of the ice is the slope at the surface, not the slope at the bottom, you might have ice that flows up, and down over hills or stuff like that, which isn't normally what happens with water. Water doesn't flow uphill. So how fast does this happen? Generally, glaciers move at rate of around 10 to 300 meters per year, so 30 to 900 feet per year. However, not all parts of the glacier move at the same rate. Like when we talked about streams, glaciers are also subject to friction at the sides. So the interior part of a glacier ends up moving faster than the margins of it. Um, so that's one thing. And then the second thing that happens is that if we have liquid water accumulating near the glacier, like for example at the base, we can have basal sliding, which we would call a surge. Basically, the presence of the water decreases the friction that the glacier is undergoing. So when this happens, you can have the glacier move from like around 10 to 110 meters in a single day. So friction very much part of the issue for glaciers moving. So we have our glaciers that move forward, but we also know that they retreat because it's very much like a hot topic uh, in like the news and stuff. So now let's look at glacial advance and retreat. So for the formation of a glacier, when we have snow, this equates to accumulation. Um, we can also have ablation, which is the removal of ice from a glacier, which can happen from melting, becomes water, goes away, sublimation, which means that it goes from solid to gas, and calving, which is when little chunks of the glacier are fall off. So because of this, we can have a zone of accumulation, which is over here, and then we have our zone of ablation. We have these equilibrium lines that divide these zones. So ablation and accumulation are both happening on both sides of this equilibrium line. However, in the zone of accumulation, there's more accumulation than ablation. In the zone of ablation, there's more ablation than accumulation. Okay, so let's look at these two concepts now. So this is our starting glacier, our reference date. The toe of a glacier is like the end of it. And here we have ablation, more ablation than accumulation happening, more accumulation than ablation. So if there is more accumulation happening than ablation, then we have glacial advance. So we have our toe of our glacier has now moved forward, the equilibrium line is now below, etc. However, if we have more ablation than accumulation at this point, then that causes our toe to retreat. It moves uphill, and then there's the equilibrium line moves uphill as well. So far we've talked about ice on land, but we also have ice at sea. So, glaciers that have their toes in the sea are called tidewater glaciers. And if it's a valley glacier that's entering the sea, so valley glaciers were these like mountain glaciers that enters the sea, we would call them an ice tongue. Ice tongues are longer than they are wide. And then if we have a continental glacier entering the sea, they are called an ice shelf. They are wider than they are long. However, not all of the ice that is at sea originates from glaciers on land. In polar climates, like for example, here we have the North Pole and the South Pole, we can have the surface of the sea itself freezing, forming sea ice. And then also, I just want to briefly, we have free-floating chunks of ice that rise 6 meters above the water and are at least 50 meters long. We would call these icebergs. Icebergs are a lot bigger below the surface, as anyone who's watched the movie Titanic knows. Um, so to wrap up this section, glaciers form where snow lasts all year and turns to ice. Mountain glaciers form at high elevations and flow down slope. Continental glaciers form at high latitudes and spread over the continent. Ice moves by plastic deformation or by basal sliding, which is the water removing friction. The balance of accumulation and ablation are the things that determine whether there's glacial advance or glacial retreat. And in polar regions, ice shelves, ice tongues, and sea ice cover large areas. Um, Give me a second. Okay. Um, we have sea ice covering large areas. Okay. So at this point, I want to stop and tell you guys the first bonus word. So in the quiz, there's going to be a few. We're going to have the opportunity for 2 bonus points for people who watch the video. So at the end of the quiz, I will ask you for these words, and you will write them in. The first bonus word is eggshell. Okay, now let's continue. So now that we've talked about glaciers and different kinds of things, now let's talk about carving and carrying by ice. So the process of glacial erosion. Um, we talked in this class of water and wind as like agents of physical weathering, and glaciers are also a very very powerful agent of physical weathering, and they form features that are very distinct. So, for example, in the image on the upper left, we have half domes, which are formed by the carving of ice. The presence of cirques and additives, which we'll see a little bit later, are also features formed by glacial erosion. And then finally, we can have really polished surfaces like the ones seen below. So now in this section of the class, we're going to talk about glacial erosion. So there's different ways that glacial erosion can take place. One of them is glacial incorporation, which is when ice just kind of like surrounds rock and then carries it away within it. We can have glacial plucking, which is when glacier break off fragments of bedrock of where it's lying on top of or passing side by side with. And then we can also have glacial abrasion. So glacial abrasion can lead to a formation of like really fine powdered rock flour, because we're literally just like the surface of rock. And one of the things that also happens with this is glacial striations. So glacial striations form because of clasts that are moving within the ice are just like scraping by. And if these striations are big enough, then maybe we might call them glacial grooves. Um, we have Now we're going to look at like stages in the development of a glacially carved mountainous landscape. So, in at before glaciation, we have V-shaped valleys, which correspond to like rivers, and we have a lot of tributaries, streams that feed into this like larger stream. Then, when there's glaciation, glaciers formed in those tributary valleys, but because of glaciation, they start to carve outwards, and they formed very specific U-shaped valleys, hanging valleys, and like spurs and horns, which we'll look at now in a little bit more detail. But this is kind of an example of what might happen to a landscape post um, mountainous glaciers or alpine glaciers. So one of them is like the Matterhorn, which is like a very famous mountain, a big challenge for rock climbers, formed as a result of like carving by ice. Here we have a U-shaped valley in the Swiss Alps. So um, a river might form a V-shaped valley, which is shown in like the smaller inset image. However, a glacier forms a U-shaped valley. And then here we have Hanging Valley, which is also kind of like um, corresponds to happens after glaciers. So after the glacier have melted away, we still have this area, this topographic low where water will flow from. But then it's just kind of like water trying to fill in the shoes of the glacier. So Hanging Valley. So these are features that correspond to like mountain glaciers. Now we're going to look at features that correspond to continental ice sheets. So um, a lot of it depends on what was there to begin with. So for example, if prior to glaciation, it was an area of low relief, then you might have very polished, flat, straight surfaces. If the area was hilly to begin with, then maybe the glacier will just smooth them out. And part of this smoothing out, um, these glacially eroded hills end up being asymmetrical, and they are called roche moutonnées. Uh, I do not know French, my bad. But basically, it's French for sheep rock because at some point someone thought that they looked like a sheep lying down. But the orientation and the look of these hills can help us indicate the direction of glacial flow. So the area that's like has like a more gentle slope is like against where the glacier was flowing. So in this image on the right, glacier flow was happening from right to left, like in the diagram. Finally, the last feature that we're going to look at are fjords. So fjords are glacially carved valleys that are either filled partially or entirely filled with water. And the reason that these fjords form is because you have our valley glacier that meets the sea, and the glacier base remains in contact with the ground until the water depth exceeds 4/5 of the glacier's thickness. These are the ones that we would call like ice tongues. Um, so they cut out much deeper than present sea level. Um, then, when the glaciers retreated and all that, the water in the glaciers went back to the to sea, it ended up flooding the area and forming a fjord. So, to wrap up erosion, so glaciers scrape up and pluck rock from its surface. They polish and scratch rock, and they carve distinctive landforms such as U-shaped valleys, cirques, horns, and an elongate bay or lake form when water partially fills a glacial valley is called a marine fjord. Now let's look at, so we've seen erosional features. Now let's look at depositional features that are associated with glaciation. All glaciers incorporate clasts at the base or sides. So the way that this ends up working is like a giant conveyor belt, and they end up transporting all this sediment in the direction of flow. Where all that sediment ends up being like deposited, we would call that a moraine. So here we have the formation of a moraine and then comparing it to that glacial conveyor. So we name moraines depending on their location. So there's like a lot of things labeled in the image on the left, but the important things that I want you to note are lateral moraines, medial moraines, and end moraines. Lateral moraines are these all this accumulation of sediment that happens at the sides of the glacier. Medial moraines form when like two glaciers like meet up with each other, and then their two lateral moraines end up in the middle of one larger glacier. So that's the medial moraine. And then finally, end moraines happen at the toe of the glacier and is where the glacier ends. And here it has like a few end moraines which correspond to like different stages in that glacial retreat and advance. But the important part is like those three basic ones. So we have a lot of different kinds of sedimentary deposits, which we like umbrella term, we call it glacial drift. So the first kind is glacial till. So glacial till is sediment that's transported by ice and it is unsorted. It is just because the solid ice can just carry whatever. So on this image, we can see an example of glacial till. So we have some things that are like sand size, which we don't really see in this image, but we can kind of imagine. And then we these like larger rocks, and we have our human as reference, as scale. We can also have glacial erratics, which are like really big cobbles and boulders that have been dropped by a glacier. And one of the reasons that we can identify an erratic is that they're not really near anything else that you can be like, oh, it fell from that mountain. It's just kind of in the middle of nowhere. And a lot of the times they end up being deposited on top of that polished surface. So that's one way that we can identify them. We can also have glacial marines, which are these clasts that are carried out to sea by icebergs. And then when the iceberg melts, then all the clasts that were contained within just mix up with the marine sediment. We can have glacial outwash, which is like when meltwater streams carry and sort the till. All that till, which was unsorted, was just kind of a hot mess. We ha- we can end up forming a braided stream, which that with that excess of sediment. We can have lurse deposits. So lurse deposits are a specific kind of wind deposit associated to glaciers, and they're formed by strong katabatic winds. I try to find a good definition for katabatic winds, but I'm not 100% sure, so give me a second. So katabatic winds are essentially winds that flow like downhill, but they're formed specifically like adjacent to glaciers, so um, like that's why it's considered a glacial sedimentary deposit. And then finally, we can also have glacial lake bed sediment. So we have all the meltwater from our glacier that's like retreating, and we have fine grained sediment that's deposited below, and we can have the formation of varves. So varves is like when you have like that layering that can correspond to like seasonal changes. So now let's look at different landforms that are associated to like different depositional landforms that are associated to glacial environments. So this is like the big one that has like a bunch of them, but we're going to go into detail with a lot of them. So for when we had our continental glaciers, so we have our toe, two lobes joined in. So here we'll have the formation of a medial moraine. We also have tunnels because of when our glaciers start to melt, we have water outflowing from them. And then, so when the glaciers finally retreat, we have a lot of different features, our moraines, and a lot of other things, which I'm going to explain now in the next slide. So, we've talked about moraines, but yes, a ridge of sediment in the northeastern U.S. is is a large terminal moraine that built up during the most recent glaciation, and it underlies Long Island and Cape Cod, Massachusetts. So all of this is a terminal moraine. Um, the next feature that we're going to look at are drumlins. So drumlins are are little hills that are formed after glacial ice reshapes underlying till. So they end up having like this little nice shape that corresponds to like the flow of ice. And so here we have a shaded relief map of central New York, and you can see all these little drumlins within. Um, Next glacial features that we're going to look at are kettle holes. Kettle holes. So kettle holes are a circular depression that is formed in the ground that is made when a block of ice calves off the toe of a glacier. It has become buried and then melts. So these are like little chunks of ice that just fell off, broke off, melted, formed a lake. And they end up, like when they happen, it's not like a singular kettle hole. It tends to happen like a lot of kettle holes. And because of this, geologists call all like the whole landscape knob and kettle topography, because we have holes and then little hills and it's like a whole thing. And then lastly, the last feature that we're going to look at are called eskers. So even though glaciers are our main agent of deposition, with the glaciers we also have meltwater. So sediment that is deposited in the meltwater tunnels when there's glacial retreat, um, they are known as eskers. So sediment in eskers is more sorted than the rest of the glacial, so that's one way that you can identify it. And it's just like a little snake, a little snake. So depositional features of glaciers. Glaciers are like giant conveyor belts and transport massive amounts of sediment. When the ice melts, sediment accumulates as unsorted till. Meltwater streams and wind transport can sort the sediment from outwashed plain gravels to loess deposits, respectively. And then deposition by glaciers produces a lot of distinctive landforms such as moraines, eskers, and kettle holes. Now that we've looked at like glaciers as like a whole and things that they do, now let's think of like the consequences that happen as a result of glaciation. So one of the things that happen is ice loading. So when we have glaciers on land, they have a weight, and they cause uh, the lithosphere to sink a little bit, because the lithosphere is more solid, the asthenosphere was like more plastic. So we have subsidence happening when we have a glacier. When the glacier melts away, then our lithosphere can rebound back into place. However, this takes a long time. Like I mentioned earlier in the video, the last ice age ended around 12,000 years ago, and Canada and the northern US are still on the rebound. The next consequence of continental glaciation are sea level changes. So glacial ice accounts for 2.15% of Earth's total water supply. And we compare that to lakes, rivers, soil, and the atmosphere, which altogether are only 0.03%. So the presence or the absence of glacial ice ends up uh, ends up resulting in a lot of sea level change. So, for example, this map shows coast, like there's a theoretical coastline. If, for example, all of the ice sheets that exist today were to melt, so Florida is gone, and a lot of other big cities are gone. But yeah, and then this red line shows the coastline when the ice age was happening. So 12,000 years ago, all the way out from like eastern Florida, all of that was still land. So presence or the absence of ice accounts for a lot of sea level change. The other thing that I wanted to mention is that it one of the ways that prehistoric humans went from the old world, like Asia, to America was using the Bering Strait because all of this was a land bridge, so they could just walk across it. Um, and this graph shows sea level rise between 17,000 to 7,000 years before Christ. And a lot of this is due to the melting of ice glaciers. So this is average sea level, and then as glaciers have been slowly melting throughout the last 16,000 years, sea level has been rising. Another consequence of continental glaciation is the effects that it has on drainage and lakes. So, for example, we can have the formation of ice margin lakes, which form like on the margins of a glacier as it's retreating. So, for here we have Glacial Lake Agassiz, which was an ice margin lake that formed at the end of the last ice age. And we can also have pluvial lakes. So, pluvial lakes are not the same kind of lakes. So pluvial lakes form, the presence of ice sheets kind of affects atmospheric circulation and like rain. And so this area received a lot more rain than it does now. And during the last ice age, there was a lake here called Lake Bonneville. Hope I'm saying that right. And as the climate there has become more arid, Lake Bonneville has evaporated away. But remnants of Lake Bonneville are what make the Great Salt Lake in Utah. And finally, we can also have the formation of periglacial environments as a result of glaciation. So, regions that are adjacent to the glaciers, but not the glaciers themselves, they have very cold temperatures. And this means that the groundwater remains frozen nearly all year. Soil that does that is called permafrost. So, the map on the left shows periglacial environments in North America uh, now. So the dark purple are the ones that have permafrost all year round. Light purple has discontinuous permafrost, and then this um, this checkered line shows like the southern limit of like permafrost during the ice age. So as you can see from this map, Ohio was very much in that periglacial environment. So the growth of glaciers can affect many aspects of the Earth system. The weight of a continental ice sheet causes subsidence of the lithosphere. Melting causes it to rebound. Continental ice sheets store water, so much water that they affect global sea level, and then the drainage of lakes related to glaciation can lead to torrents and etc. Now here comes the second word. The second word is, oh, sorry. The second word is pumpkin. Okay, now let's continue with the rest of the class. So now that we've seen the consequences of glaciation and how these affect the environment, deposition, erosion, now let's talk about what ice ages are and like how the role of like, well, yeah. So the last ice age is the Pleistocene Ice Age. It started 2.6 million years ago and ended around 12,000 years ago. During that Pleistocene Ice Age, there was the Laurentide Ice Sheet, and it covered all of Canada east of the Rocky Mountains, and it flowed southward over the northern U.S. It was made up of distinctive ice sheets: the Labrador Ice Sheet, the Keewatin Ice Sheet, and the Baffin Ice Sheet. Um, but as you can see, it wasn't just North America. We also can see them in like Europe and Asia, and we have sea ice, etc. So this was the last ice age. Life during the Pleistocene was very different from what it is today. So one of the ways that it was different is that all the climate belts were like lower than you have them today. So, for example, all the way to Louisiana we had deciduous forest, and we had cypress in Florida, and all of these like polar regions were much more south than they are today. The other way that it was different is that most of the precipitation was like located northward, feeding the glaciers, so tropical rainforests weren't as rainy. Um, so if we look at the first Ice Age movie, you can also see that like animals were very different. They were adapted towards living in the Pleistocene. They were very furry and fluffy, much bigger, and life and climate was very different. Um, However, the Pleistocene Ice Age wasn't just like, oh, everything is frozen and that's it. Um, Geologists have found paleosols, which are ancient soil deposits, and rock beds containing warm fossils of warmer weather animal and plants laid between distinct layers of glacial sediment. So, because of this, we can say that ice sheets advanced and retreated more than once during the Pleistocene, and we would call these glacial and interglacial periods. Um, in the U.S., they identified five different glaciation periods, and in Europe, I think they identified four, and then they named them like depending on like which area they kind of found them. So that's why Wisconsinian end moraines, Illinoisan end moraines, etc. So, like I mentioned, on land, Europe and North America, geologists identified 4 to 5 glaciation periods. However, in the marine record, they found 20 to 30 different glaciation periods. And how did they do this? They reconstructed this using the composition of marine fossil shells, which, like we've mentioned earlier in the course, most of like marine organisms like corals and like different shells are made up of calcium carbonate. So um, there's two different, well, for using this, we're looking at two different isotopes of oxygen. A heavy isotope, which is oxygen 18, and a lighter isotope, which is oxygen 16. During during glacial times, there is more. Uh, Give me a second. Okay, sorry about that. So during glacial times, there is more O18 in these fossil shells, and during interglacial times, there are less. So this is how they were able to reconstruct all of these glacial and interglacial periods. Sorry. Okay. Um, so when we look at the fossil record, we can see that this Pleistocene ice age was not the only ice age. Um, we have ancient glacial deposits of like tillites and stuff, or glacially polished surfaces that let us know that there were other ice ages. So here we have like a very, very small geologic record that goes from present to 4 billion years ago. And we can see a few different ice ages. So here, Pleistocene, late Paleozoic, late Proterozoic, and there's a few like smaller ones. Um, of note is this late Proterozoic ice age. We term that snowball Earth. We call this because we have tillites occurring at equatorial latitudes, aka we have tillites, glacial deposits in what would be the tropics. So the theory is that the entirety of the Earth was covered in ice sheets. So during the Pleistocene, uh, we have an ice age. It went from 2.6 million years ago to 12,000 years ago, and we have ice sheets that advanced and retreated up to 30 times. The record on land is less complete than that in marine strata, for evidence of only 4 or 5 major glaciations are preserved on land. Ice ages also happened earlier in Earth's history. During the late Proterozoic, ice may have covered all of Earth. So, um, Now the question should be why? Why is this happening? So um, we can think of long-term causes and short-term causes. So compared to like all of the record, ice ages happen like pretty rarely, which means that the appearance of ice ages are linked to major tectonic or evolutionary events during Earth history. So there's like a lot of different theories that kind of explain why we might have the formation of ice ages. So one of them is that we can have plate movements of continents moving towards higher latitudes, and so we just have more surface area to form ice. We can have higher latitude. Can have those continents in the higher latitudes over upwelling zones, which means that there's going to be like more volcanism, higher land elevation, which can also lead to glaciation, mountain glaciers. We have that the volume of mid-ocean ridges decreases, aka they're like smaller, which leads to the formation of larger ocean basins and less shallow seas. And because there's less um, shallow seas usually moderate temperature. We can have island arcs that block warm ocean currents to reach higher latitudes. We can have organisms that extract CO2 from the atmosphere, and since they're extracting CO2 from the atmosphere, they're cooling the atmosphere. We can have chemical weathering on land due to mountain uplift. Weathering absorbs CO2. That is a whole, it's a wild theory, guys. But it's super cool. We can have volcanic activity increases, which leads to the increase of aerosols in the atmosphere, blocking the sun's rays. And we can also have that uplift of mountain belts, maybe changing atmospheric circulation. So basically, a variety of different like tectonic things can happen that could lead to the formation of ice ages. However, when that that these long-term causes kind of explain this graph over here, which leads to the formation of an ice age. However, once we have an ice age, we have a lot of back and forth of what's actually happening. So we have short-term causes that control glaciation once their ice age has already started. So now let's look at short-term causes. So once an ice age has started, for whatever reason, continental glaciers advance and retreat many times, and there is a periodicity to these changes. So like yeah, like every few years it kind of changes back and forth. So it's not happening randomly. So in 1920, a Serbian astronomer and geophysicist Milutin Milankovic published work that provides the basis for an explanation. And this is going to get a little bit um, complicated. No, it's fun. Okay, so Milankovic Milankovic started studying um, these changes and ended up finding different cycles that correspond to like orbital changes. So one of them is the eccentricity of Earth's orbit. So the eccentricity of Earth's orbit refers to like whether the orbit around the sun is more circular or whether it's more elliptical. And he says that this happens every 100,000 years. So this affects whether the Earth spends part of the year farther from the sun or closer to the sun. The next cycle that he described was obliquity. So obliquity refers to the tilt of the Earth. So the Earth is not like completely vertical. It's not like at zero. It's slightly tilted to one side. And so it changes from 22.5 degrees to 24.5 degrees. And when this is these changes in tilt lead to um, seasonal differences in the higher latitudes. So, for example, when tilt is greater, the difference between like you can have the difference between like a really hot summer and a really cold summer, and then when tilt is not as great, you can have like a mild summer and like an okay-ish winter, for example. And then the last cycle that he described was precession. So precession is a 23,000-year cycle, and it affects the relationship between the timing of the seasons and the position of the Earth around the sun. Um, and it's also called like the wobble of the Earth's orbit. And we can compare it to like a spinning top. So the way that this top is doing like that, that's the same thing the Earth is doing, only that it does it taking 23,000 years. Um, so when we combine all of these different cycles together, this affects the total amount of insolation, so the amount of radiation that we receive from the sun at the surface of the Earth. So when geologists started to study the climate record, they found these cycles that Milankovic predicted, and we call these the Milankovitch cycles. Um, However, the Milankovitch cycles are not the whole story to explain why glaciation happens or not. So, for example, other things that affect or trigger, amplify a glacial advance are changing albedo. So, albedo refers to like the reflectance of an object. So, an object that oh, give me a second. Sorry. Okay. So, um, objects that have high albedo reflect more sunlight. So, for example, um, snow is white, so the sunlight reflects off. No, not concrete. Like a road, for example, is like darker, so it absorbs more sunlight and it's hotter. So if it's reflecting, it's cooler. If it's absorbing, it becomes hotter. Another thing that could affect glacial advance is the interruption of the thermohaline circulation. So thermohaline circulation was that big, um, deep ocean current that kind of circulated water throughout the entire planet. And if it's not working properly, then, for example, it doesn't moderate temperatures. Other things is biological processes that change CO2 concentration. So if we have like an organism that absorbs CO2 or puts out CO2, that affects glacial advance. And then finally, solar variability. So this obviously doesn't have anything to do with like the Earth itself, but the sun has different cycles of how much radiation is inputting and outputting, and that could also affect glacial advance. So now that we've seen different causes for ice ages, for the formation of ice ages and these glacial and interglacial cycles, let's look at what happened for the Pleistocene ice age. So one of the things that happened for the Pleistocene ice age to occur is that there was long-term cooling during the Cenozoic. The Cenozoic being the geologic era post dinosaur extinction. So, which should be around here. So here's like dinosaur extinction. And though we had like a real this like high Eocene high temperatures, overall they started lowering. One of the reasons that this started lowering, or at least one of the reasons that people think that this happened, is the uplift of the Himalayas and the Tibetan Plateau. So the formation of this mountain change changed atmospheric circulation and allowed for cooling. One of the other things that happened is that the formation of the Southern Ocean. So Southern Ocean is this ocean like in between Africa and Antarctica, and it separated Antarctica from like warmer currents, so it allowed this to just become cooler and cooler and cooler. Also, I want to note that this is not to scale. Antarctica is a lot bigger than this, but this is um, a ball, so it's not supposed to be accurate. So we had cooling throughout the Cenozoic, but still that leaves like a 40 million year gap that we didn't have an ice age actually form. So why did the Laurentide ice sheet form 2.6 million years ago? One of the reasons that geologists believe that happened is that the gap between North America and South America closed with the Isthmus of Panama. And this stopped warm Caribbean waters from going into the Pacific. So now these warm Caribbean waters had to flow northward with the Gulf of Mexico, the Gulf Stream, and this provided a source of precipitation to the British Isles. So basically, it was cold enough throughout the Cenozoic to have an ice age, but Until this happened, they just didn't have enough snow happening to allow the formation of glaciers. So this is like long-term thing that happened to allow the Pleistocene Ice Age to happen, but there's like advances and retreats. So what I have here is not like 100% what happened, but it's kind of an example of what could have happened. So, for example, the mountain cleavage cycles allowed for dropping temperatures in northern Canada and allowing snow to remain unmelted during the summer. The snow reflected sunlight, becoming colder, and then allowing the formation of a glacier. So the glacier kept growing because of the positive feedback of the snow albedo. Positive feedback is a feedback that kind of like allows it to grow. You know, it's like um yeah, it's it keeps feeding into the same thing. However, the weight of the glaciers then caused the lithosphere to sink, and when the glaciers were at lower altitude, they started to become warmer, and then sea ice started covering the oceans, cutting off our source of moisture. So the success of the glacier in stage two ended up becoming its demise. And then as the glacier started retreating, albedo decreased, so we didn't have snow, and it started getting warmer and warmer. And then finally, since sea ice melted, we have our source of moisture again. However, the rain could have accelerated the rate of ice melt, so sorry, so it led to faster glacial retreat. So this is one of the ways to kind of explain all these like advances and retreats throughout the Pleistocene. So will there be another glacial advance? So looking at the periodicity of like glacial and interglacial cycles during the Pleistocene, they occur every 10,000 years. And it has been 12,000 years since that last glacial period. So it's like, oh, are we going to get an ice age? So yes, no. So um, during the medieval times, we had the medieval warm period, and following that, we had a little ice age. So little ice age was a kind of brief period, a few hundred years, that allowed the advance of a lot of glaciers in Europe and North America. And like for example, um, it allowed for rivers to freeze in the Netherlands, and then this is when ice skating became a thing in Netherlands, which I think is kind of cute. Um, but we had a little ice age. However, oh, and here we have that during the little ice age, we had a glacier filling this valley. However, most of this glacier has vanished, and most of the retreat has happened in the last century. So here we have a map of Greenland, and we have where we had frozen areas in 1996 in white. The things in pink melt during the summer but freeze during the winter. And so as of 2012, none of it stays frozen the entire time. So because of other things outside of interglacial and glacial cycles, um, we are not in a little ice. We are not in an ice age currently. Um, However, some just gonna go to the next slide. Ice ages are triggered by the distribution of continents, ocean currents, atmospheric CO2. We have advances and retreats controlled by Milankovitch cycles, and we may be living in a super interglacial period, and like super interglacial as in like it should have been a glacial period, but now it's just we have an interglacial period that's just become a lot longer than we we might expect. Um, so after this lecture, we've distinguished between glaciers and other forms of frozen waters. We've recognized different types of glaciers. We've explained how they flow and which factors explain the direction that they flow, the processes of glacial advance and retreat, and why they happen. We've distinguished between lots of different kinds of sea ice. We've described the process by which glaciers erode landscapes and characterized depositional landforms near glaciated regions. We've explained how glaciers cause subsidence and how there's like rebound, and we've explained what an ice age is. So next week, Monday, April 29th, we will start talking about global climate, and we'll get into like a little bit of like why we thought we should be in an ice age, but we're not currently. So I hope you guys enjoyed the lecture. There's a quiz for this. Don't forget the two bonus words, and have a great rest of the week.